All right, so here in Unit 8, we're going to be talking about a lot of the same things that we talked about, at least initially, with our vectors, but now we're going to be dealing with them in 3 dimensions, okay? So before we actually get to the vectors in 3 dimensions, we do need to look at just simply plotting points in the 3-dimensional space, okay? So as we look at this, you can see we have an X, Y, and Z axes, all right? And the dotted parts are like the negative sides of those axes. But graphing these can be a little bit challenging because you're trying to do something 3-dimensional on a 2-dimensional piece of paper, all right? And that's always kind of challenging. So I want to just practice graphing a couple of points. You are not going to have to do a ton of graphing, but it does help to at least try to visualize what's going on here, okay? So 2, 3, negative 4. I want to start, first of all, actually, kind of illustrating this with you here. Let's say that right here is the origin, all right? Right in this cone. And we'll use the grid on our floor here with the tile to help us out. So if we're graphing 2, 3, negative 4, okay, let's say X goes this way, Y goes this way, and Z is going up and down. So to get 2, 3, negative 4, I'm going to go over 2 spaces here. Okay, so there's a positive X, and then I'll go 3 spaces this way. There's 2, 3. But then to go to 4, if 0 is right here about at my waist, negative 4 might be on the floor. Okay? So you could, that's how you have to try to kind of visualize what these points are doing, okay? It's not just a movement over and up, all right? It's not just rise and run anymore if we're talking about slope. Now we'll have actual velocities that have 3 different components, okay? Now, if I'm going to sketch this, watch how we sketch it, all right? Just watch for one, and then we'll let you guys practice 1 or 2 here, okay? When I'm sketching things in 3 dimensions, notice first of all the X is kind of coming out towards me, and then Y is kind of going left and right. And I know it's a little bit weird to get used to because we're used to Y going up and down and X going left and right. But we've kind of taken that whole graph. You know, here's our Y pointing up, here's our X pointing over, and we kind of just laid it down, okay, like this. Okay, so if you put your hand up like a L, like loser, there's your X and Y. And then if you lay it down, rotating your thumb towards you, your X is now pointing towards you, your Y is now pointing left, right, and Z is going up and down. So when I go to graph this, all right, I need 2 along my X. And I'm going to mark my X-axis. Here's 2 units. And notice how when I mark it, I kind of try to make it parallel to the Y. Okay? And then for my Y, the Y is 3. So I'm going to go 1, 2, 3 along the Y-axis. Okay? And then here's where it's helpful to kind of draw where those are. So parallel to the Y, I'm going to draw this X equals 2, and then parallel to the X, I'm going to sketch this Y equals 3. Okay? And now you can do the Z one of 2 ways. Okay? The Z needs to be a negative 4. So I can go back to the origin and go down 1, 2, 3, 4 units. Okay? And then if I look at it, if I were to draw like up and down here through this intersection I've already got, I need to do that same distance, this distance right here, down from that point. Okay? So I'm doing this distance, but I'm doing it down from here So there's the point that I'm looking for. Okay? Does that make sense? All right. So this point P in this case is kind of coming out towards us a little bit, but it's down below the surface, 4 units. Okay? All right. Let me illustrate one more and then I'll let you guys just try one here. So again, P, if I'm doing 4, 5, 6, I go along the x-axis, 1, 2, 3, 4. I go along the y-axis, 1, 2, 3, 4, 5. So I draw that kind of parallel to the x. I draw this kind of parallel to the y. Okay? And then the z is supposed to be a positive 6. So 1, 2, 3, 4, 5, 6. I measure that distance straight up here. Okay? So that same distance is going to put me right about here. And that's the point 4, 5, 6. Now, as you can probably guess, if I didn't draw any of these little hash marks or the dotted lines, you would have no idea where that point was. I mean, that could be like on the x, y, and z could be 0. You know, we could have like a negative x and a positive y, and z could be 0, just looking at that on a flat surface. So that's why these little dotted lines are important to draw, so we know where we're at. Okay? Ethan, did you have a question?
So the order of the coordinates is x, y, z?
Yeah, it's alphabetical, so that makes it easy to remember. Just like you had x, y, now it's just x, y, z. Okay? Alright, so take a minute, try to plot this one here. Point Q is 3, 5, 1. Alright, so let's work this out here. We've got a 3 on our x, so 1, 2, 3, and I got to put like a dotted line parallel to my y-axis here. Okay? And then y is 5, so 1, 2, 3, 4, 5. So again, I'm going to kind of go parallel to the x-axis here. And guys, this point right here is actually the point 3, 5, 0. That point where you're finding the intersection, that's 3, 5, 0. Okay? So to get 3, 5, 1, we have a distance of 1 here. So we're going to go straight up 1 unit. And that's our point 3, 5, 1. Okay?
Why does it look so much better on yours than mine?
Yeah, see.
Well, I've done this for a while. I should be a little bit better than you at it. So, but here's the thing, like, part of this is it needs to be kind of the best that you can get it. If you keep those things parallel, all right? If you keep those things parallel the best you can, that really helps, okay? But I'm not expecting you to be fantastic artists, okay? But who knows, it might help you kind of learn perspective a little bit. I was a horrible artist until I took Calculus 4, and I had to graph a whole bunch of stuff by hand in 3D, and I actually learned a lot about like perspective drawing and stuff as a result. So now I'm a mediocre artist. So, but yeah, that's how we will graph those points in 3D. So let's talk about, now that we kind of have an idea of what's going on here, let's talk about connecting what we've learned about vectors to the third dimension. Okay? So first of all, our unit vectors, I and j. Now we have a unit vector k. Alright, so we have I, j, and k. And you'll notice now we have 3 components to each vector, not just 2. So we have the horizontal, vertical, and z, or yeah, you have your x, y, and z components that we're dealing with here. So I is no longer just a 1, 0, it's 1, 0, 0. And j is 0, 1, 0, and k is 0, 0, 1. Alright, so that's one thing that you can do here. Another thing is, remember we said you could write any point as a position vector from the origin? Okay, so I could write this point P as a position vector OP, and I could make it with the parentheses, just the way you see it. But the other three types of notation also work in 3D. Okay, so we could use the angled brackets, 2, 3, and -4. Okay, one that we start using a whole lot in 3D because it actually kind of makes it easier to draw all three or to write all three is that parentheses where we just put them vertically. So 2, 3, -4. Okay, especially when we have expressions for some of our components and whatnot, as you'll see when we get to parametric equations. We end up using that notation a lot. But then you also have the IJK, the unit vector notation. So we have 2i plus 3j minus 4k. All right? So that notation is very similar. Okay? All you're doing is adding that third component. All right? Pretty easy so far, right?
Yep.
Okay? All right, so if you know last unit, this part of this unit shouldn't be too tough. Another thing that we did is if we 2 points, we found the vector between those 2 points. Okay? This is where students who didn't really learn the concept struggled. Okay? If all you were thinking of was rise and run with the vectors in 2 dimensions, you may have a little bit of trouble here making the leap, okay? So pay attention here. If we have 2 points, A is the point x1, y1, z1, and B is the point x2, y2, z2, okay? Then when you are trying to find the vector from the one point to the other, you always take the coordinates of the point you're going to, and you subtract the coordinates of the point you're coming from. Okay? You see how that works? And by the way, notice we're using that vertical parentheses notation. This is partly why. It's a lot easier to kind of have them all right there stacked than to have it spread all the way down a line on your paper. Okay? So, we have our position vector. In this case, it's the position of B relative to A. And I can sketch this real fast here. A is the point 1, 1, 2, 3, 4, 5, -2. So here, there's 1, 5, and then I go down 2. So there's my point A. Once you get the hang of it, you don't quite have to write as many of those little dotted lines. All right, and then B is the point -3, 2, and 3. So here I'll put B. I have -2, 3, and then 3. 1, 2, 3, up. Okay, it's going to put me right about here for B. Now, just looking at this vector can be a little bit tricky because it just looks like it's going straight up. All right, but the reality is A is kind of closer to us while B is kind of in the background, so it's kind of sloping away from us. Okay? But that's the nice thing about it. If you learn it with the formulas and stuff, even if it's hard to see, you can still work it out, no problem. All right, so vector AB, to get the components, we take the coordinates of which point first?
When we're going to.
The one we're going to. So -3, 2, 3, and we're going to subtract the
5, -2.
good, the 1, 5, -2. Okay? So this gives us -4, -3, and +5. Okay? So there is our vector from A to B. If you were thinking rise and run, and you can really think of that in terms of movement, then you can still use that concept. Yeah. To go from 1 to -3 is a -4. To go from 5 to 2 is a -3. To get from a -2 up to a +3 is a +5. So you can use that, but sometimes people struggle because it's not something you can really see that easily. Okay? Is everyone with me?
Yes, sir.
All right, good. So, last thing here is the magnitude. The magnitude of vector AB. Now you'll notice here, in our formula, they have AB equals, and by the way, notice you can use this notation, because if you remember back from geometry, that just tells us the distance from A to B, which is the same thing as the magnitude of the vector from A to B. Okay? So, you can use that notation too. But they have the x-coordinate minus the x-coordinate squared. Alright? Well, this is just the x component of the vector. Alright? This is just the y component of the vector, and this is just the z component of the vector. So, for example, if I wrote AB as ABC, like this, then I could rewrite this formula and say, okay, the magnitude of AB is the square root of A squared plus B squared equals plus C squared. Okay? It's just like in 2 dimensions, A squared plus B squared, but now we have that third dimension, C squared, that we got to add in there as well. Okay? So in this case here, the magnitude of AB we would find by taking the square root of -4 squared plus a -5 squared plus, or I'm sorry, -3 squared. Right there. Plus 5 squared. Now, there are no triples in this case because we need a quadruple. Alright, I don't know any of those. I'm sure there are some, but okay. But if you do all the squares, it adds up to 50, so we got the radical 50. And that would be a 5 root 2. And you can just leave it in radical form, where that's like 7.1 or 7.07, I think it was. Okay? Any questions? If you know your stuff from last unit, the first part of this unit at least should be really, really easy. Okay? You're just adapting your knowledge to an expansion to the third dimension. Okay? So, I've given you some practice with these. Okay, find the distance from the origin, in other words, the magnitude of its position vector. Okay, here are some other problems. I tried to give you some that had a little bit of a twist to it sometimes, like show that those are vertices of an isosceles triangle.
So we have to find the magnitude from all of them, show the two sides are equal.
Okay, you need to find the vectors that make it up, find the magnitudes of those vectors, and show that at least 2 of them are equal. Okay? So, it'll take a little bit of thought there, but tried to give you some problems that were a little bit more thought-provoking, a little more interesting. Okay? Also here, notice we've got a little bit with number 13 that's a little bit more, trying to determine what A, B, and C are in those cases. Alright, if the 2 vectors are equal, then what do we know? Same magnitude, true.
Oh, their components are equal.
Their components will be equal. Alright, so if 2 vectors are equal, their components are equal. You can use that idea to help you find A, B, and C on number 13 there. Okay? So, not all of these ones that are shown here are in the required IP, but you do have, in the required IP, you have a number of these, okay? And again, remember, all of the answers are in the back of the SL textbook, okay?